Hey kids, doing a brief video production on scientific measurement and introduction to it. And we will be focusing on the metric system, types of observations, and prefixes within the metric system. So I looked up the definition of science on the internet, which may seem funny to you being that I'm a science teacher, but I was just curious. I wanted to know what it said. So it says it's the intellectual and practical activity encompassing the systematic study of the structure and behavior of the physical and natural world through observation and experiment. So it is the study of the world around us through making observations and through experimenting. So if you look at how the public perceives science, it seems like they think it's pretty simple. And you can go back to your middle school days and think of FIAC, the scientific method. And it's very, very simple and straightforward. You have a problem, you create a hypothesis, you do some experimentation and make observations, and then you make some conclusions and communication. So kind of like this. I wonder, I have a question. So the challenge is accepted. So developing the hypothesis needs some work. You need to read about it, and then doing the science, and then coming up with a conclusion. Well, in reality, science is not that straightforward, and it doesn't always look like that. In reality, it looks a little bit more like this. So, I wonder, here's my question. Challenge accepted. Look at all of the different pathways we can take from there. So reading about it, doing the science, realizing that it's not quite going as expected, feeling that you get amazing results, and then realizing that your results were as good as lint, and then going back and doing more science, resulting in the instrument breaking, becoming very, very frustrated, asking yourself what's going on, realizing that you think that you know a lot, and then you realize that you didn't know as much as you went, or that you thought. So the essence of this is that science is really messy. And students often think that their experiments don't work if they get results that are different than their hypothesis. But that's not true at all. Their experimental results are your experimental results. They're neither good nor bad. So some of you will experience this disgruntledness when we do our STEM symposium projects this year, and that's just normal, and it's to be expected, and it's how we learn. So if you look at this smattering of things on the screen, I pose a challenge to organize these in two ways. Let me take that back, into two categories. So when I ask students just to organize it, they come up with all different kinds of categories, but I'm just going to keep it simple because I want to keep this pretty short today. So I told students to organize it into two categories, and very quickly they said, well, it's measurements and descriptions. Well, that's okay, but I will respond to them and say, every single one of these is a measurement, because you can measure how shiny something is. You can say that one object is longer than another. You could talk about a degree of sharpness of an object. You could measure various shades of red. They're not equated, they're not related to numbers, but they're still measurements, they're still observations. And they're equally as important. So the types of observations that we make, so just going back to that definition of science, science involves studying the world through observation and experiment. So the types of observations that we have are quantitative, which are numeric, they include a number and a unit, and qualitative, which are non-numeric and descriptive. Going back to this list, you'll see that we could categorize them into those which contain numbers and those which contain just letters. And our numeric ones are our quantitative observations, and the non-numeric ones are our qualitative observations. Now, they are equally important, and my goal this year is to really allow you to grow in your ability to make really good observations. So both types are equally important during scientific investigations. So with the experimentation, it will usually involve developing a hypothesis. Now you've learned about a hypothesis definition since you were itty-bitties. So it's a testable statement. It's an educated guess. It's an educated guess because you need to educate yourselves. Before I allow you to make a hypothesis in a scientific investigation, you need to find out if other similar experiments have been done, what their results were, because then you can get a good sense of what might be likely to happen and the results you can expect. So a hypothesis is an educated guess. 99% of the hypotheses that we develop will be developed as an if-then statement. There are some times it's just a little bit too difficult and we have to craft the hypothesis in a different way. And that happens sometimes. But typically, you ask yourself, if you change a variable in an experiment, so you're controlling changing this thing, then you want to see how something's going to respond. So if this is changed, then the system will respond in a certain way, whatever way you predict. Now, one thing that I want to point out to you is that I want you to stay away from using the word prove or proof or proven, because we don't prove things in science. In science, it's an investigation through observation and experimentation, and we gather evidence. And the evidence is data that can either support or not support the hypothesis. And again, the data is just data. It's not good data. It's not bad data. I mean, if the data was collected in a scientific fashion, we don't consider it bad if it doesn't support your results. It just is what it is. But stay away from the word proven, because we don't prove things. We gather evidence and we see if that evidence supports any claims that we make or any hypotheses that we make. So the metric system, and I told students they didn't need to write this down if you are watching this and copying notes. This is just some background information. The metric system is also known as the SI, or International System. And it was embraced so much by the French revolutionaries that they wanted to have every single month be 30 days because it was divisible by 10, and they also wanted to extend the work week from 7 days until 10 days. So it's based on this unit of tens. Now, the International System was adopted in 1960 at a conference on weights and measures. Now, people needed to meet because they were communicating in different ways, and that prevented some major barriers. So they decided that they needed to all speak in the same language, and they called this system the International System. I can't pronounce this, but I found a pronunciation on the internet, so I'll just put my microphone over there and see if you can hear it. I apologize in advance if this makes a big ruckus. I'm sure it is making a ruckus.
Système international d'unité.
Système international d'unités.
Système international d'unité.
I have a tough time.
Système international d'unité. Système international d'unité.
That's pretty slick. So, let me bring my microphone back. Maybe I'll just let it sit on the table here so you don't hear all of the scratchiness. I hope that you can still have good sound quality. Okay, so the metric system, or the SI system, has 7 base units, and most other units are derived from these 7. We also use units like liters and Celsius that are not considered part of the metric system, depending on who you talk to. We are going to treat the liters and degrees Celsius as part of the metric system. And it looks like I started to modify this PowerPoint a little bit and I didn't finish. So what I was going to say here is that some will consider liters, milliliters, degrees Celsius as part of the metric system, and we can too. So in the metric system, with these base units, prefixes are used to represent quantities that are either smaller or larger. And you can see I made the text a little smaller, and I like to say smaller or larger than the base unit. So these are the SI base units. We have length, mass, time, temperature, the amount of substance, electric current, and luminous intensity. These 5 are ones that we're going to use regularly in chemistry class, and this is what I asked students to copy down in class. So the base unit of length is the meter. The base unit of mass is the kilogram. It bothers me a little bit that they have a prefix here, and it's not just the gram. I don't have control over that, nor do I understand why. The base unit of time is the second, and temperature is Kelvin. Even though most of our measurements take place in Celsius, many calculations involving temperature need to have all positive numbers. So the Kelvin scale is used. It's an absolute scale. There are no negative numbers. And then our good old friend, the mole, you can see that it's been shortened up significantly here by dropping the E. We will use that a lot. Some of you may use electrical current or luminous intensity if you have a STEM project that involves looking at measurements of those things, but we won't be doing that specifically as a class. When we look at the prefixes, this table is a summary of them going all the way from tera, which means 1 billion, to atto, which I am not sure what this is. I know that nano is 1 billion. This is maybe 1 trillion. I'm really kind of failing miserably right now at this explanation. But we don't need to know anything beyond nano. You will be responsible because I have noticed that there are some severe weaknesses in student understanding of the metric system. We need to really internalize the meanings of these prefixes into our working everyday language. So you need to know that kilo means 1,000 and hecto means 100 and deca means 10, and this is our base unit. Deci is 1/10, centi 1/100th, milli is 1/1000th, and then micro and nano are even smaller. So all of these are smaller than the base unit, and all of these are larger than the base unit. These are the ones I had students copy in class, and I expanded upon their meanings. So the prefix kilo, the exponential factor is 1 times 10 to the third. Our abbreviation is K, and it means 1,000. So if you have a kilogram, it means that it is 1,000 times larger than a gram, which is your base unit. If you have a decameter, it is 10 times larger than a meter. If you have a centimeter, it is only 1/100th of a meter. It is 100 times smaller than a meter. So you can see in this chart the meanings, their numerical equivalents, and their exponential factors. And you will be responsible for knowing abbreviations, exponential factors, meanings, both in terms of a number, and also this concept of prefixes relating to things that are larger than the base unit and also smaller than the base unit. So one thing I do want to point out, most of these abbreviations are pretty straightforward. This one right here is the Greek symbol mu, and it's kind of got a little tail on it. It looks like a U, and it has a little tail on it, and that's the symbol for micro. So this concludes what I discussed in class for this lesson, an introduction to the metric system, a discussion on observations, the types, including quantitative and qualitative observations, and how they're equally important, and also that the metric system is based on it's based on units of 10. There are 7 base units. These are the 5 that I want you to have a good working knowledge of. I want you to internalize this. I want you to study. I want you to memorize, as well as these prefixes. So that's my introduction to the metric system, and we will continue to work through it rather extensively throughout the course of the year. Thanks for watching.